Okay, the goal of this video is to prove E equals mc squared. This is a kind of a different kind of proof than you usually see, but we're going to start with the derivative of hyperbolic arctange. Um, and we start by just giving the statement, the definition of, this is v over c is beta, that's your velocity, it's the slope of that's described by hyperbolic tangent of the angle phi here. So this is just a definition related to the relationship between velocity and rapidity. So we're going to take the derivative of both sides of this equation, del del b of beta, del del b of tanh phi, and at the end of this, del del b of beta is just 1, and over here on the other side we use the chain rule. You get del tanh phi, and del phi del beta. Notice we don't really know anything about the result. It's just using the chain rule to describe what happened. So now actually we've isolated del phi del beta at this point, which is actually what we want. The hyperbolic arctange is del phi del beta. And so that was kind of a cool trick we just did there. So then we break out tanh phi. Tanh phi is sinh phi over cos phi. And then the derivative, and then we use the old derivative of quotient law here. Derivative of the quotient is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. And that the other part remains. And cos squared phi minus sinh squared phi is 1. And we've taken the del phi del beta and flipped it and put it on the other side, so we get del beta del phi. And then you can do some trigonometric work to see that 1 over cos squared phi is 1 minus tanh squared phi. I don't know why I continued after this. We've already got it. Del phi del beta is cos squared phi. So you could have stopped at line F because you've got what you want at this point. So I decided to revise the last few steps of this derivation, and instead of involving all of those y's and t's, I just decided to solve step E for del phi del beta, which means multiplying both sides by cos squared theta over 1. And then in the next step, I just give a couple of other expressions for cos squared phi, which would include 1 over 1 minus beta squared and 1 over 1 minus tanh squared of phi. Okay, so now knowing that the derivative del phi del beta is cos squared phi, it may be of interest to see what happens when we think about the equation of relativistic force. Now, the impulse momentum law states that delta p is equal to the net force on an object. Basically, the change in the momentum of an object is equal to the net force on it times the time that net force is acting on it. Here, the equation that has been solved for the instantaneous net force has been solved for the instantaneous net force on an accelerating object or particle. So just basically taken this equation here divided by delta t, or dt. Part B, it says the Newtonian definition of P equals mv equals mc tanh phi has been replaced here with the relativistic definition of P equals mc sinh phi. So instead of putting mc tanh phi, which would just be mv, we're putting mc sinh phi. Step C, we're applying the chain rule to this whole thing. We're taking the derivative with respect to time. I think I'll put parentheses around that. Okay, the problem with step B is we don't know what the derivative with respect to t of this thing is. So I'm going to separate it out by, first of all, taking del phi mc sinh phi, which we can calculate. But then, since we made del phi, we need to make del phi del beta, which we have already calculated. And then after that, I'm going to put del beta del t in order to put it in terms of the del t. And so this is kind of an application of the chain rule. We're doing 3 derivatives instead of just 1 because we know what these other derivatives are, and we can take a ratio between the 3. So now in step D, we're applying this derivative to mc sinh phi, and it's just mc cosh phi. Step E, we are applying the identity we just figured out in the previous equation. Del phi del beta is cosh squared of phi. So we're replacing del phi del beta with cosh squared. Cosh phi times cosh squared of phi is cosh cubed of phi. And then we still got that del beta del t in there, but we're going to replace the del beta del t with, before I take del beta del t, let's move this c from over here to over here. And now we can take del beta c del t, which is the derivative of the velocity with respect to time. And okay, so I moved the c from over there to over here, and now beta c is the velocity. So del v del t is acceleration. So this is our equation, basically, cosh cubed of phi times mass times acceleration. And you can also write cosh cubed of phi as square root of 1 minus v over c squared cubed, or you can write it as gamma cubed times mass times acceleration. Okay, the next part of the derivation, we're going to try to calculate the relativistic kinetic energy. We start this by saying that we're going to calculate the amount of work done by the force is the integral of the force over a distance. Now this distance, how am I going to break this down? Well, we have from our previous derivation that the force is gamma cubed mass times acceleration. Acceleration is the speed of light times del beta del t. And then we just leave that del dx there. So this is a little bit of a weird step, but we're just gonna like swap these, put the dx over here and put the del beta over here. That's all I did. And then I made one other change. Instead of going from 0 to the final position, I'm making del beta my variable of integration. So I'm going from 0 to the final velocity. Okay, so next step looks like I've replaced dx dt with just c times beta, and that's all I did there. Dx dt equals c beta. And then in the next step, I'm preparing for step F by separating out beta gamma, there's beta gamma, times gamma squared, there's gamma squared. Still have, and I'm separating out del beta. I'm just kind of introducing a del phi over del phi here. So I'm going to start doing it in terms of initial and final rapidity. So I should change my variables of integration there. So instead of going from 0 to beta final, we're going to go from 0 to phi final. Okay, so what do we got here? Well, we have from earlier calculation that del beta del phi is, well, it's the reciprocal of del phi del beta. And del phi del beta, we know from is the derivative of the arctangent. So reciprocal of the derivative of the arctangent is 1 over cosh squared phi. So now these two things just cancel out. That cancels out with that, and we're just left with mc squared integral of sinh phi d phi. And integral of sinh phi is cosh phi. We plug in our 0, we plug in our final rapidity, and we just end up with a simple expression of mc squared cosh phi final minus 1. So in the end, we get this calculation of mc squared cosh of phi final, which is cosh phi final, and then cosh of 0, so that's minus 1. And this is the exact expression from that we get from assuming, what did we assume? We assumed that the momentum was mass times the speed of light times the hyperbolic sign of phi, which is different from the difference between that and the Newtonian expression. Is the Newtonian expression replaces the sinh with a tanh. We also assumed work equals force times distance. That didn't change. There's no change in work equals force times distance. It just came out to be a different quantity down here. Because when we plugged in force is, and yeah, that was another thing we used. Del P, force equals del P del T. So we used, so now that we've got this value for kinetic energy, let's talk for a second about the physical meaning of the rest mass energy. Now, notice that we have not really actually, we don't really actually have any particular meaning for the rest mass energy. But we do have this strange thing that we're just subtracting cosh phi minus 1. The rest mass energy is in that 1. So while the math kind of dropped out the rest mass energy of mc squared with that minus 1, we don't really have any particular phenomenological prediction of how that rest mass energy should manifest itself in the universe from this derivation. But we can draw a diagram and say, okay, if the momentum times the speed of light is here, we can draw the kinetic energy here, we can draw the rest mass energy here, and we can draw the total energy here. But what we don't have is like any phenomenological manifestation of the rest mass energy or total energy. We just have, but we do have phenomenological manifestations of kinetic energy and momentum. So I'm going to take a second here to describe the graphs of kinetic energy versus velocity, and let's see, kinetic energy versus rapidity. So in the kinetic energy versus velocity, you can see that the Newtonian kinetic energy with respect to velocity is just 1/2 mv squared. That's this black line here, and that is just a parabolic approximation of what kinetic energy you would get. You can't actually get that velocity because, well, you can't get a velocity past the speed of light. On the other hand, the relativistic kinetic energy, it has an asymptote here at the speed of light. Let's look at that one. Relativistic kinetic energy with respect to velocity. Basically, it's got that mc cosh phi minus 1, and phi is arctange of v over c. And when you have that formula in there, it asymptotically approaches infinite kinetic energy at a velocity of the speed of light. So now I'm going to look at the things with respect to rapidity. So I've changed the horizontal axis label here to rapidity, and we can see that the relativistic kinetic energy with respect to rapidity is mc squared cosh phi minus 1, while the Newtonian kinetic energy with respect to rapidity is still 1/2 mv1, or is still 1/2 mv squared, but we're also defining v to be a function of rapidity, which is c times the hyperbolic tangent of the rapidity. And so in this case, increasing the rapidity to infinity does not allow the velocity to get over 1. So the Newtonian kinetic energy, it starts out here being similar, but then the velocity just approaches the speed of light, and the kinetic energy for the Newtonian case, as the velocities go towards the speed of light, don't actually change that much. But when the rapidity changes for the relativistic kinetic energy, it goes up and up and up.